Welcome back, everyone. So we're going to look at the last two examples for the related rates notes. So these are going to be slightly more challenging examples overall. So the first is a water trough problem. So you're going to have a similar one in your textbook as well. A water trough is 10 meters long, and a cross-section has the shape of an isosceles trapezoid that is 30 centimeters wide at the bottom, 80 centimeters wide at the top, and has a height of 50 centimeters. And if the trough is being filled with water at a rate of 0.2 meters cubed per minute, we want to know how fast the water level is rising. So another water level rising problem, instead of a cylindrical cone that we're filling with water, it's going to be this water trough that has an isosceles trapezoid for its cross section. So let's go ahead and draw it. So if we're looking at one end of it, it's going to look like an isosceles trapezoid. It's going to go out 10 meters. There we go. Let's clean it up a bit. Okay. And note we're filling it with water, but we'll note those dimensions. So we've got 30 centimeters on the bottom, 80 centimeters on top. The height is going to be 50 centimeters, and then it's 10 meters long. So the first part that's really going to be what you want to do is make all the measurements the same. So you can convert everything to meters or everything to centimeters. To deal with smaller numbers, I would recommend converting centimeters to meters, as I put in the hint here, but you can always go in reverse as well and make the meters into centimeters if you wanted to. So if we go from centimeters to meters, we need to divide by 100. So we'll get 0.8 meters, 0.3 meters, and then 0.5 centimeters. So again, dividing by 100 will give us the correct dimensional conversion to meters. So it might be useful to just redraw that cross-section, similar to what we did with the cone, and then look at the relationships between those lengths. And note we're filling it up with water. So what we're going to end up with then is two separate vertical measurements that we're looking at here. So we'll note the height is going to not be fixed, right? So you have h on both sides. This little section on the outside here is also not going to be fixed. So maybe we call that x. It's not really a radius, but you could call it r, I guess, if you wanted to, but I'll just call it x. And then this value in between, though, is going to be fixed, right? So this this length across here is always going to be the same, and it is the same as the base, which is 0.3. So this is 0.3 centimeters. And then up at the top, we're going to have, of course, this will be 0.3, and then we need to get 0.8 in total. So we'll have 0.25 and 0.25 on the outsides there. And of course, we have the height is 0.5. Okay. So let's think about our volume equation then. We know volume is going to be the equation we have to work with. So the volume is length times width times height, or base area times the length. Now the nice thing is that we know this is 10 meters, so that's fixed. So the length of the trough is fixed. So then our volume is going to be the base area of our cross section, which is that isosceles trapezoid, times 10. So let's see if we can figure out what the base area is. So that is going to be 1/2 base 1 plus base 2 times height times 10. So that is the area of a trapezoid. So we take the average sum of the bases times the height in order to get it, but we need to figure out what B1 and B2 are. So we can see that if we let this be base 1 is just 0.3, but then all of this is going to be base 2, so we need to add those lengths. So it's going to be 2x plus 0.3, it looks like. Okay, so let's put that in. So we're going to get 1/2, and then we'll have 0.3 plus 0.3 plus 2x times the height times 10. So now we have it in terms of h and x, our measurements. But we want it to be, again, in terms of one variable, I'm going to multiply the 1/2 and the 10, so that'll be 5. And then we'll have 2x plus 0.6 times h. So now we need to get h in terms of x. And again, we can use a proportional relationship. So h is to x as the height is 0.5 and, oh, whoops, sorry. Let's go back here. So we'll note at the very top, x is going to be 0.25, and then the height itself will be 0.5. So it's going to be 0.5 over 0.25. And if I look at my equations here, I want to figure out how fast the water level is rising, which means I want this in terms of h only, which means I need to substitute out x. So I'm actually going to solve for x here. So we know that h equals 2x or x equals 1/2 h. And then we're going to substitute that in. So we'll substitute that in. So we'll get v is equal to 5. So then 2 times 1/2 h is just going to be h times h. So we'll get 5h squared plus 0.6 times 5 is going to be 1.2, let's see, 6 over 10 times 5, 3. It's going to be 3. Okay. So 5h squared plus 3h. All right, so then we'll differentiate with respect to time, and we'll have 10h h prime plus 3h prime, which then we can factor out. So, oh, and what is our volume? Our volume is 0.2. So let's see. And then h is 30. Okay, or 0.3. So we've got 0.2 is equal to 10 times 0.3 h prime plus 3 h prime. So 0.2, and so 0.3 times 10 is just going to be 3, so we're going to have 6 h prime. So then h prime is going to be 0.2 divided by 6, which is 2/10 times 1 over 6, going to be 1 over 30. So 1 over 30 meters per minute. Let's check our units. Yeah, yes, per minute. All right, so our answer is going to be 1 over 30 meters per minute. I kind of had to squeeze it in on the right there, but clearly the height is changing at a very slow rate in terms of meters, because if it's 10 meters long and it's only, 50 centimeters high, you're still going to have to put in quite a bit of water in order for that height to change. Okay. And so our last example, we've got two triangles here. So we have two sides of the triangle have length 12 meters and 15 meters. The angle between them is increasing at a rate of 2 degrees per minute. So we're given degrees here, so we can work with degrees. So we want to figure out how fast the length of the third side is increasing when the angle between the sides of fixed length is 60 degrees. Okay, so we're going to have a triangle here. Zoom in a little bit. So we have a triangle. We've got 12, 15. This is going to be theta in general, and then this is our unknown side x. We know that d theta dt is 2 degrees per minute. Yep, 2 degrees per minute. And then we want to know when theta equals 60 degrees. What is dx dt? So we need to figure out dx dt. So let's note the first thing we're going to want to do, convert to radians. Because we don't want degrees floating around as a measurement. And so we're going to use radians because radians are unitless. So 60 degrees is just pi over 3 radians, which we know. And then 2 degrees, again, we can multiply by, pi over 180, and we'll get pi over 90 radians per minute. Okay. So now the question is, what's our equation? What's the equational relationship here? So we don't know if this is a right triangle. Could be, but we're not given enough information to say that it is, which means we have a possible non-right triangle. So how do we deal with non-right triangles and their side lengths and angles? Yeah, there's 2 different ways we can. One would be law of sines, and one would be law of cosines. So if we look here, we have two side lengths and an included angle, which would be side angle side. So we could try law of sines if we wanted to, but remember, law of sines is going to require us to have at least 2 angle measures. And we only have 1 angle measure, or we only have 1 angle that we're dealing with. And when it's specifically 60 degrees. So this is going to be a case where we have to use the law of cosines. So for the law of cosines, is going to look like, in general, just remind ourselves here, a squared equals b squared plus c squared minus 2bc cosine of a, where a is the angle opposite little a. And note this is a right triangle, gives us just the Pythagorean theorem. So this is just a variation on the Pythagorean theorem, or you could actually think of this as the general case, where the Pythagorean theorem is the special case, where this is equal to 0 when a is 90. So we're going to need to use that formula. So we're going to have, since we're solving for x here, we're going to have x squared is equal to 12 squared plus 15 squared minus 2 times 12 times 15 cosine of theta. Okay. And the nice thing is that the derivative is going to work out pretty nicely here. But we do need to figure out what that third side length is. So let's figure out the third side length first. So the third side length is going to be the moment when theta is equal to 60. So we'll get that x squared is equal to 144 plus 225 minus 12 times 15 is going to be 144 plus 36. So 160, 320, I believe. And then cosine theta is pi over 3. So that's going to be 1/2. So x squared is going to equal, let's see here, 369 minus 160, which is going to be 209. So x is going to equal rad 209. Okay, so not a nice integer value, but still an answer that we can use. All right, so we've got rad 209 for x. So let's go ahead and now we're going to take our equation and differentiate it. So again, we have x squared equals 12 squared plus 15 squared, which aren't going to matter. So let's go ahead and differentiate with respect to time. So we'll get 2x x prime, and then we're going to get that 12 times 15, which is going to be 320, negative 320. Oh, but we have the derivative, yeah, times negative sine theta, theta prime. Okay, so the negative sign is just going to cancel and become positive. And so we'll have 2 rad 209 x prime equals, actually I think we can divide by 2, just make that 160. Let's do that. So we'll have 160. So sine of theta when theta is 60 degrees is going to be rad 3 over 2. And then theta prime is pi over 90. Okay, so then x prime is going to equal all of that stuff. So let's go ahead and, so we'll get rad 3 times, let's see if we can simplify this a bit. So that'll be 80, and then that'll be 8 over 9. So we'll get 8 rad 3 pi over 9 rad 209. And then at this point you could estimate using a calculator if you wanted to. Or just leave it exact, and that is going to be centimeters per minute, meters per minute. So definitely a messier answer overall. Let me double check that 12 times 15 just to make sure. Oh, it's 360. Oops. That is going to throw everything off. So let's go back. So that's going to be 360 because that's 180. Yes. So again, the 2 and the 1/2 will cancel, so that's minus 180. So maybe this is going to be nicer. Let's find out. So I have 369 minus 180, which is 189, which is not going to be any nicer. So we get rad 189. Okay, so let's do this again. We'll just put 360 cosine theta. All right, so we get 2x x prime equals 360 sine theta times theta prime. Again, the negatives will cancel out, and then we'll end up with 2 times rad 189 x prime equals 360. Sine of 60 is rad 3 over 2 times theta prime is pi over 90. All right, so let's do some nice cancellation here. So we got 180 divides the 2, and then this 2 will cancel and become 90. Oh, so much nicer. And the 90s cancel. So we end up with x prime is equal to rad 3 pi over rad 189 meters per minute. Oh yeah, that's much nicer. So apologies for the error there, but you can just skip through it. So we'll end up with rad 3 pi over rad 189 meters per minute. So, you know, law of sines, law of cosines, definitely something you should review. Dealing with, nice geometric shapes. So isosceles trapezoids, isosceles triangles, right triangles with specific isosceles relationships. So 45, 45, 90, 30, 60, 90. As well as circular shapes, maybe a pentagon or hexagon here or there as well. So for all of these questions, the more examples you do, the better, because it'll kind of help you develop that equation identification skill along with differentiating. But note, all of these examples can get messy. So the numbers are going to get a little bit messy as well, so just be very careful with your work. On the last page, it's got kind of a walkthrough of what you should do to set it up. So I think that's helpful to read through as well. But again, if you have questions, come by my office hours, shoot me an email. And